Welcome back. So today's day is going to be dedicated to the data-driven methods. As always, we'll have 3 one-hour lectures followed by lunch and then a tutorial and a plenary talk in the evening. Our first speaker is Professor Adway Mitra from IIT Kharagpur. He's going to talk about machine learning for monsoons. And as you can see, he's already has a nice acronym, ML4M. Thanks, Adway, for coming all the way.
Okay, hello. So, good morning, everyone. So, I am Adway, as already mentioned, and I am from currently working in IIT Kharagpur. But before, I am entirely from machine learning, computer science, artificial intelligence background. So that way, I may be like a bit of a outlier among all the speakers whom we have met so far, and but I started working in this domain of climate in general and this Indian monsoon in particular, and my that journey started here when I was a postdoctoral fellow here in ICTS itself. So it is always good to come back here and speak about what I have been doing for the past few years. So before I begin my talk, as we already discussed in my brief interaction with you all yesterday, so some of you are, or I guess almost all of you are like working in the domain of climate sciences or atmospheric sciences. So the language you are familiar with may not necessarily match with the language which I am speaking. So if there is anything which you are not understanding, or if I am using some jargon which is not familiar to you, please feel free to interrupt me right there itself. So the motivation for this talk is like art system models. So like art system models, of course, you are all familiar with. When we are so we essentially are living in the times of climate change, and like when we want to understand what is our future, what is going to happen to us, our climate in the next few decades or so, then we all use the simulations by these art system models. Now these art system models, of course, these are coupled models. There are so many different components: land processes, atmospheric processes, ocean processes, and so on, each of them represented by a large number of these differential equations which represent our understanding of the physics of those processes and also the coupling between those equations. So building an art system model based on based on our knowledge of the physics, that's of course a formidable task, and it requires collaborations among scientists from all domains. And the models themselves are also extremely computationally expensive. They require these supercomputers to run and so on and so forth. But even then, if we see the different art system models like the GCMs and other models developed by different research groups, we will see that they often don't agree with each other. Not only do they not agree about the future, but they often even don't even agree with the past. Why is that the case? That's the case because of basically our limitation in understanding the physics of the process, and it could also be due to the spatial resolution. So we know that all these processes in the atmosphere, they take place at different spatial and temporal scales, but not all of those scales can be resolved by the models, especially when there are these subgrid processes for like at scales below the model resolution. Then these models are not able to explicitly represent them. So it's usually done through some kind of parameterization, and those parameterization, as we know, is not necessarily correct. So one specific application of this is of course weather forecasting. Now yesterday we heard Professor Rajivan's talk about the past, present, and probably also the future of weather forecast in India, specifically with respect to Indian monsoon. And he also introduced us to like various types of weather forecasting systems. So here, when we talk about climate sciences in India, we have like in recent times, we have a few stalwarts in our mind. So Professor Rajivan is definitely one of them. Another stalwart was Professor B.N. Goswami, whom I guess many of you may have met at some point. So a few months earlier, we had the pleasure of having him in a talk in IIT Kharagpur, which was specifically about the topic of hybrid physics AI models for Earth system modeling. And there he gave this keynote talk, a talk which many of the participants mentioned is the best talk they have heard in their career and so on. So like he of course, Professor Goswami has built his entire career, is extremely illustrious career, developing various of these physics-based weather forecasting system and so on. But right now he recognizes the potential of AI and in bridging various loopholes which are present in the weather forecasting systems which are currently in use. So these are some of the points he had highlighted in which ways AI-based systems, or at least if certain modules of these weather forecasting system can be outsourced to AI, these are the few aspects in which he believes it can be improved. So one of these things which he mentioned is assimilating data, let's say, from other sources, including satellite data and so on and so forth, as well as and very important issue which he pointed out is the issue of these accumulating errors. That is, once a system makes an error, then in the next step it will make a little bit more error on top of that, and in the next step even more error, and these errors will keep on getting accumulated, and ultimately the result you will get is way off what it should be. So this is one important issue which he had flagged. Apart from that, of course, the issues of parameterization, which I just mentioned, and also the issues of resolutions. So these are matters in which he believes that there is a significant amount of loopholes in the operational weather forecasting systems, and he believes that AI has the potential to solve them. So these are some of the recent, we would say, revolutionary developments that have taken place related to weather forecasting using AI. These ForecastNet, Pangu Weather, GraphCast. So these are all some machine learning based weather forecasting models which have been able to reach at least as well, and in some cases even better than traditional weather forecasting systems based on physics. Of course, one can always say that they tend to do well only for certain specific types of variables, or only in certain specific regions, or they may have a limited lead time and so on. But they have definitely the results of which they have published has definitely been some sort of an eye-opener for the weather forecasting community in general, and Professor B.N. Goswami is very keen about this aspect. So like I was earlier mentioning, that when it comes to these Earth system models, I mean, weather forecasting is of course a very specific thing where you are trying to predict the weather variables for we know that it can be done at several scales. There are these seasonal, sub-seasonal, daily, even hourly weather forecasts are available. Now, when we are talking about little more into the future, let's say for the past few decades and so on. So this is once then of course we have to go for these CMIP6 models. And as I said earlier, that these CMIP6 models, they carry different. There are of course a large number of models in the CMIP6 family, and many of them have make simulations of the worldwide climate in the past and the present, but they are not necessarily very accurate, and there are some phenomena which many of them represent quite well. For example, the El Nino Southern Oscillation, that cycle is represented quite well in most of the models. But then there may be more specific processes like the Indian monsoon, which may not be that well represented. So there was a lot of research which took place a few years earlier. At that time, the CMIP5 was the main state of the art. So many different types of biases. The most famous is the dry bias, case in case of Indian monsoon, which many researchers have flagged. And what you are seeing is this was my own work which came out in 2021, where I tried to see the spatial patterns of the Indian rainfall. So many of you must be familiar with this MISO, the monsoon interseasonal oscillation. So we know that the spatial distribution of rainfall across the Indian landmass evolves during the entire season. There are these active phases when some parts of the the landmass receive rainfall, other parts remain dry, and then there are break phases when the exact opposite happens. And there are also many sub phases like that. So this study basically shows that all those spatial patterns which are found in the actual observations are not necessarily reflected in the simulations by these CMIP6 models. There are some the way they represent the spatial distribution of rainfall over the Indian landmass is not necessarily the way it actually is. So all these things motivate us to look for machine learning based methods for Earth system models. So these are some of the points in which I believe, which are also in line with the points which Professor B.N. Goswami made earlier. So I'm just rephrasing those a little bit. So now let's start let's try to dig deep into some of these methods, and especially for the benefit of those of you who may not have much of a previous background in machine learning. Let's start a bit from the basics. Let's first understand what machine learning tries to do, and then we will see some specific cases of what it actually does in the context of monsoon and climate. So as you know, machine learning is not necessary. I mean, the application of machine learning in domains like climate sciences is relatively new, but it started off mostly as a subfield of computer science. And one of the most one of the best known usages of machine learning is for image recognition. So let's consider this seemingly trivial challenge that we have a large number of images. So some of them are of cats and some of them are of dogs. And now, given a new image, you will have to classify it whether it's either a cat or a dog. So whenever we are talking about any problem like this, we first must decide beforehand what is our input space, which is called, or let's say what's our input space, what kind of inputs shall we give to our machine learning model, and what is our output space, namely what kind of outputs we expect from it. So one word of caution here. So when we are from now on, I will be using the word model mostly to mean machine learning models, not these Earth system models, unless explicitly stated. So please don't get confused about that, because machine learning model and Earth system model may mean very different things. So when I say input space, so in the specific problem which I mentioned, the input space is basically images of cats and dogs. Now you can then also we need to be more specific. That is, images means what's the size of the image? Is it like a 600 cross 400 image, or is it a 1000 cross 1000 image, or is it like a 20 cross 20 image? So that the resolution of that image also has to be fixed beforehand. Is it are we talking about these color images, that is RGB images, or grayscale images? Although these kinds of things need to be fixed beforehand. So that is how you define the input space. Now, the other side is the output space. So these kinds of images are what you will give to your machine learning model or algorithm. What do you expect it to say? So clearly, if in this case, you expect it to say either cat or dog. So in this case, your output space has just two things, cat or dog. Or if I want to encode it in binary, let's say cat mean one, its output space is just 1 and 0. 1 may mean cat and 0 may mean dog, or vice versa. I mean, depending on whether you like cats or dogs. In my case, it's always 1 means cat, because I'm a big cat person. So in this case, the first thing that happens is, when you give these images, the first thing that must happen is the inputs. I mean, be it images or something else, it first must be represented as what is called as a feature vector. So how will this is an image, how will it be converted into a vector? So okay, so for starters, it's not necessary, not always necessary to convert it into a vector. There are models which can take matrices. I mean, the image is represented in a computer as an image. So as a matrix. So there are some models which like their input is just some kind of matrix. So whatever data you have, if you convert it into a vector or a matrix, it can be you can provide it as an input to the machine learning model. So but let's just for say that we have converted these images somehow into some vectors. So it, like in some cases, these vectors can actually be created with the help of manual experts. So let's say that there is someone who pulls out certain features from these images. Let's say how many, like, can you see eyes, can you see these whiskers, can you see tail, or various features as we understand, like as humans, features of that image. In general, instead of this being as cat dog classification problem, if it were a scene classification problem, let's say you are given some images and you have to say whether it's a sea beach image or a desert image. So in that case, the features might be different depending, like, let's say what kind of objects you can see in the image, can you see some sand in the image, can you see water in the image. So these could be some possible features, but these are all features which are interpretable to us as humans. But in many cases, that kind of features are not available, especially because we have say huge amount of data, and it's not possible for a human being to annotate the features in each of them. So what they do is, there are some mathematical transformations which they apply on these kinds of images, say different kinds of filters and so on. So that is something which the signal processing community can tell you about. So those filters carry out some kind of mathematical operations on these images and provide to you this kind of vector. So the vector, in that case also, each element of the vector, we will consider it as a feature of the image, though as human beings we may not be able to make much sense of what that feature actually indicates. So anyway, so basically we have our inputs, we have reduced them to feature vectors. So now what must happen is we must give our machine learning model plenty of examples of both classes, or both the categories, cats and dogs in this case. If there are multiple classes also, then for each of the classes we have to provide multiple examples. So you are basically, that's why this is called as supervised learning. It's like you are the teacher and you are training the model to say something by providing it lots of examples. So you provide these kinds of examples to the learning algorithm. With each example, you also, each feature vector, you also provide the corresponding label. That is, whether it's a cat or whether it's a dog. So now this information which you are providing to to this algorithm, what the algorithm will basically do is it will define some sort of a mapping from the feature space to the label space. That is, the feature space now is no longer images, but these kinds of vectors. So if there are the way it has been written, it's like d-dimensional vectors. So the input, let's say d-dimensional real vectors, though that need not be the case, but let's just assume it's the case. So the input is the d-dimensional real vectors. So the algorithm provides you some kind of a function f, such that if you apply that function f on a d-dimensional vector, you will get either a 0 or a 1. Now that function, what is the nature of that function? So it can be something like it can be a parameterized mathematical function, like let's say some kind of linear function or sigmoid function, something like that. Or it can be it's not something which is which can be expressed as a mathematical polynomial or something like that, but simply a step of some algorithm which you follow. Let's say each of those features you compare with some threshold, do some logical operations and or something, and somehow reach an answer. So that if you consider this algorithm called decision tree, some of you may be familiar with decision tree, irrespective of whether you know ML or not. So decision tree is like it's not really it does not really define a mathematical as a parametric function to you, but it gives you a sequence of steps, basically some logical operations which you must perform in a particular sequence, and then you will get an answer. Or it can be something like linear regression, that is W transpose X plus some bias. So like you have this input vector, you like take its inner product with some other vector of coefficients, so that way you get a real number. Now that, but you must report as either 1 or 0, so you put some threshold on that real number. Let's say 0 is the threshold, so if the number is positive, then you just report 1, and if the number is 0, then you just report as 0. So like it can be like, or it can be something more much more complicated nonlinear function as well. So whatever it is, some function f your algorithm will give you. What kind of function it will be depends on the specific nature of the algorithm. Now once you have got the function, then you must validate it. So how good is your function on unseen data, on the data which you have not provided to the model for the for this calibration purposes. So what does that so why does the learning algorithm need this kind of this data at all, the label data at all? That is basically to tune the to estimate the different parameters of the function which it is trying to find out. If it is a linear regression kind of thing, I just mentioned, you just take the inner product of these vectors with some coefficient vector. So what are those coefficients? So there are again algorithms for estimating such coefficients. If it were a decision tree, as the way I was saying, then as I said, each of the features are to be compared with some threshold and some logical operation in some sequence. So what sequence, which features, what threshold, what logical operations? So all those things will be decided by this learning algorithm based on the data which you provide as input. So based on that, let's say it has given you a feature, a function. Now you will see how good that function may be working well specifically on the observations which you have provided. But what if or how does it do to another unknown image which it has not seen so far? Some image in the same domain only, not from some other domain. That won't make any sense. You cannot provide a model with examples of cats and dogs and then expect it to do let's say a tiger versus snake classification problem. That won't be useful. So you will have to validate it with respect to that particular problem only. So you will provide it the image of a new image of either a cat or a dog, and then see how its performance is. Not just one, but several of them. That's called as the validation phase. And let's say that you find that most of those examples are being misclassified. That is, cats are being called as dogs and dogs are being called cats. Or maybe it's, it's always saying the same class. It's always saying cats, or it's always saying dogs. So there is then, then the training basically has not been good. The parameters it has, so it might mean that either the function f, which it is trying to fit on this data, is simply not enough to represent the relation or represent any meaningful relation from this input space to 0, 1. So it has to so you have to choose a different function. Now, if that is the case, then this algorithm will not do. But it may also happen that the same function but a different choice of parameters may lead to better performance on the validation. So so what happens is, like once you do the validation and you measure its performance, you basically give a signal to the learning algorithm that okay, your performance is good, or no, your performance is bad. And accordingly, if it hears that its performance is bad, then what it does is somehow it tries to update the parameters in the hope that it may improve. And this process goes on till till it is convinced that the learning algorithm is convinced that it can't do any better. That is, given the functions which it is capable of representing, it has already found the best possible choice of parameters. Now, then you see the performance again on some other held out data, that data which was not presented to it while training. And if you see that the performance is still bad, then you have to understand that this class of functions is simply not good enough for this classification. You have to move over to a different algorithm, or you may be satisfied that okay, now I have found the good performance. Okay. So whatever it is, the most important task is, first of all, you decide your inputs, what kind of inputs you want, what kind of outputs you want, and what do you want as a good criteria for measurement of success. So like in case of the example I showed, the cat versus dog classification problem, the answer is pretty obvious. It's classification accuracy. I mean, how many times you that is, to any new example, how many times you are able to predict its label correctly. That is, you call as a cat and a dog as a dog. But if, let's consider a slightly different problem. Let's say that what I am trying to, our output space is not just binary, but let's say the space of real numbers. So that's typically called as a regression problem. So in that case, the number which you predicted, let's say it is 6.3. Just giving an example, while the actual desired correct answer is 6.5. So strictly speaking, 6.3 and 6.5 are not equal, but they are still pretty close to each other. So it's possible that you may not consider this as a big error at all. Or it could be that you actually require very high precision. So 6.3 and 6.5, you may consider it as a big difference. So it all depends on context. So it is your job then to specify what is called as a loss function in the jargon of machine learning. Basically a function which compares the predicted and the desired results and gives you a number which somehow quantifies how big your error is. If the loss function gives you a big number, that means you have made a big error. If it gives you a small number, it means you have made a small error. So now, specifically when we are talking about in the context of climate, or even more specifically in the context of monsoons, so these are some of the questions you may want to ask. First of all, how many predictor variables? By predictor variables, I mean these feature vector. Your feature vector, as I mentioned, is a d-dimensional vector. So what is your d? And what is your d, and what are the specific features that you are looking for? If you remember, Professor Rajivan in yesterday's plenary talk showed us this equation. So this is the equation for the 16 parameter statistical model, which IMD had been using for quite a long time. So as the name suggests, it has 16 predictors, 16 input variables, which are represented by these xi's. So what are these xi's? So these are various climate-related measurements from different parts of the world, which the climate scientists of that time thought would have a direct impact on the Indian monsoon. So your input space in that case was a 16-dimensional vector containing those values. And what is your output space? The output you are looking for is this number R. What is this number? This number R here is the ISMR, that is the amount of rainfall that will take place over the Indian landmass during the JJAS months. That is the ISMR. Now, of course, sometimes some people also refer to it as AIMR. Some other people define ISMR specifically with respect to the monsoon zones, and variations are there. Let's just stick to the total JJAS rainfall over the entire landmass. Now, what are the parameters of this model? The parameters of this model are these bias terms C0, the individual coefficients C1, C2, etc. for each of the predictors, as well as these exponents P1, P2, etc. So as you can see, this is a non-linear model. It would have been a linear model if all the PIs were equal to 1, but probably they are not. So the task of your machine, if we were to frame this as a machine learning model, so I do not know what techniques IMD used to estimate these parameters, but if we had to do it like using machine learning, I would again will provide the lots of data the observations of these predictor variables and the corresponding ISMR in those years. So and then define a suitable loss function, and then there will be some algorithms which try to choose these parameters in a way that will minimize that loss function. But as you were seeing, this is this particular approach is limited in multiple ways. So why limited in what ways? First of all, as you can see, it is one thing is rather obvious. It is only a particular form of this. The F which we are talking about, it has a very specific form. Now, if the best relation between these predictors and the ISMR, the Indian rainfall, is more complicated than this, or it's not, or it cannot be represented in this way, then there is, of course, no way this model is going to give you a very good answer. That is one obvious criticism. Another criticism could be that the inputs are just some 16 real numbers, and the output which you are getting is also one real number. So one may ask that. So there are, many climate scientists will agree with this, that the total amount of rainfall over the Indian land mass is not necessarily a very useful quantity for anyone. Because it hides a lot of details. It may indicate, for the same amount of rainfall in two different years, one may have rainfall evenly distributed all over the place. No region has excess or deficiency, or it would be that some regions are having floods while other regions are having droughts. Or it could be that it may be uniformly distributed over the 4 months, or it might be that 3 of the months are dry, had hardly any rainfall, and in 1 month it rained like hell, and it made up for the deficiencies. So all these details are hidden away if we are looking to represent the Indian rainfall over with just one number. So you may want to make this output more explicit. Say, for example, you, instead of trying to predict just a single number, you may want to predict something like a spatial map of rainfall, predict the monsoon rainfall over the entire region. Or you can also want a spatiotemporal map, that is at different points of time rather than over the entire season. Like, let's say on day 1, on 1st June, which region will get how much rainfall, on June 2, which region will get how much rainfall, and so on. So what you are seeing here is the outputs from forecast net, which is one of the well-known AI-driven weather forecast models. So it is giving you spatial maps of wind speed in meters per second all over over the American region, and at different lead times, from t equal to 0, 18 hours from that, this is what the wind speed map over US will look like. After 36 hours, this is what it will look like, and so on and so forth. So the input, the output you expect from these models is these kinds of spatial map, and that also at different time points. So it's a spatiotemporal prediction problem. So that's as complex as this whole thing can get, while this, you can say, is as simple as the whole thing can get. And in between them, there are multiple steps. It might be that for the whole season, you may want just one spatial map. You must be all aware of the IMD forecast. So at the these IMD monsoon reports. So at the end of every monsoon season, IMD publishes a map showing which regions received how much excess rainfall, how much deficient rainfall, and so on. So it's, in that case, it's like you are getting one single map as an output. That or it might be as a time series, that is on different days how much rainfall happened. So all these different kinds of outputs are possible. Similarly, there can be different kinds of inputs also as possible. Here 16 real numbers are the input, but it could also be that your inputs are also some spatial maps of some other variable which you think can be a good predictor for the monsoon, be it the sea surface temperature or whatever it is. So depending on what kinds of input you want to put in and what kind of output you expect, you can frame your problems and your model in different ways. So this is again what is known as a neural network. So neural network basically is you can call it as a computational, it's as a concept which can be used to represent different kinds of mathematical functions. So the neural network, of course, it has the input layer, which is all the input variables you are providing, and the output layer, which is the output variables you expect. But this function, the f which I mentioned, which maps the input variables, the input space to the output space. So these functions, I mean, all the mathematical operations that are involved in evaluating that function, it's done in a distributed way in different layers of the neural network. So let's look at this simple function itself. So your input layer will have all these values. So the first step might be to raise each of these to a certain power. Now this can be done parallelly. That is, x1 is raised to its power p1, x2 is raised to the power p2, and all of these 16 things are done parallel to each other. They do not dependent on each other. But once you have done that, then you multiply each of them again by a coefficient. C1 is multiplied by, the first input output is, you can call x1 p1 as the first temporary output, x2 p to the power p2 as the second temporary output, and so on. So each of those temporary outputs are then again, they undergo one more operation. They are multiplied by these coefficients. So that gives you the second layer of intermediate steps, intermediate results. Then the third layer, where you add all of these things together and then add the bias term. So you are doing some operations parallelly. That is, these things like raising each of the inputs to the power p1 and multiplying them by this coefficient c1. So those things can be done in parallel. But then there are some things which have to be done strictly after, one step after the other. So that is represented as, so those things which can be done in parallel, you can represent them as different nodes in the same layer. So this is one layer, calculating those powers, they may be considered as the first layer of operations. The second layer of operations may mean multiplying each of them with their corresponding coefficients, the C1s. The third layer, if it exists, here it's not there, but if it is there, that may mean adding all of them together and then adding the bias terms. So the whole operation, the whole function, we are just reducing to these sub steps, some of which can be done parallelly and some of them which must be done but in a particular sequence. So this, what the neural network really does is, it helps you to group all the operations which you must do into parallel components, which you call as different nodes in a particular layer, and into a sequential structure, which you call as different layers of the neural network. So here there is one hidden layer. This hidden layer basically represents the intermediate results. So here is only one hidden layer, but after this I can add one more hidden layer. So these intermediate layers will, the intermediate results will undergo one more round of operations to produce the second round of intermediate layers. Then if I may want, then I can add a third hidden layer, which will carry out another intermediate results. And then in each of these layers, there can be these nodes which represent how many operations like this you are doing one after the another. So what happens in each layer? So each layer basically does a very simple operation. It's basically whatever values it receives from the previous layers, it just multiplies each of them with a particular number, which is represented by the weights of these edges, and then it adds up all those numbers. That is what is the operation that is done in each of the layers. And after that, there is some nonlinear function which is applied onto that result. So that is called as an activation function. So that's, it could be linear function also. There is no reason why it should be a nonlinear, but it's usually called a nonlinear function. So basically, what the output which you get is some linear combination of all these inputs with some simple nonlinear function applied on it. So, and like all of these layers, the same thing will take place. But these weights, they may be different for the different nodes. So in this node H1, it receives inputs from X1, X2, Xn, all of them, but it will have its own set of weights associated with them. So this maybe I'll call them as W11x1, W12x2, and so on. Similarly, H2 will again receive all these inputs, but it may have different weights for them. I may call these as W21x1, W22x2, and so on and so forth. So that is why each of them will do essentially the same thing, but in a different way. And then I can have one more layer when I will do the same thing, and so on. So the neural network is like doing what it is doing is it's calculating an arbitrarily complex function by reducing them to like a few canonical steps, which are sometimes done in parallel, sometimes done sequentially. So that like the whole calculation is reduced to something like a distributed framework like this. Now, there are some specific types of neural networks which are called as convolutional neural networks. There are other versions also, which really depends, which really denotes what is the particular operation that is being done at these layers. So as I said, like in each of these nodes, it basically calculates a weighted sum of its inputs transformed by with some nonlinear function. But what does that? What does it really mean? What does this output mean? So what it really means is, of course, dependent on the weights which you provide. If the weights are provided in a certain way, it may mean one thing. If the weights are provided in a different way, it may mean something else. So there are some specific types of structures one can impose on these neural networks, which force each intermediate result to simulate one mathematical operation which is well known. So and particularly common form of that operation is the convolution operation. So convolution is a mathematical operation which is very common in signal processing. So it's basically you provide a filter and you have an input, so you slide the filter over the entire input. So what is the purpose of doing it? It really depends on the context. It may mean it's a very noisy image and you want to smoothen it. So it's like every value you replace it with a like a mean or something like a mean or weighted mean of its neighboring values. So that way, if there are some noisy values standing out, so that noise can be rubbed out by smoothing it by bringing the impacts of the spatial neighbors. Or if you want to detect certain patterns, then you represent that pattern with this filter and just slide it all over, seeing where the values match that particular pattern. And if the match happens, then the filter will give a high output. If it does not match, then it will give a low output. So these are only two examples. Convolution can be used to do many different things, but it is found that like if we arrange all these weights in a particular way, in a particular structure, then what the output of this hidden layer will be is essentially the result of that is carrying out a convolution operation on these inputs with the help of a filter. The structure of that filter will determine what weights you put on these layers. So that is called as a convolutional neural network, or the CNN. Or it can also happen that the data or the input which you are providing is a sequence. That is, here I was talking about a single vector. Now, instead of considering it as a vector right away, you can, or it could even be a matrix. Instead of providing that vector or the matrix right away, you can. It might be in some cases that the input is a sequence. So let us say that you provide, we will give some concrete examples of that. Let's just say for now that you have your, the input which you are providing is a time series of some or atmospheric variable, and you expect the output as, let's say, the amount of rainfall which the Indian landmass receives. So now, because the input is a sequence, you don't provide it the whole thing at a same time, but you do it step by step. So initially, like you provide the first value, let's say at t, the value at t equal to 1. That may be either a single real number or it can be a vector something. You provide it as an input to the model, or to the neural network. So it does some kind of transformation of it and calculates some intermediate value. So that intermediate value is stored. Next, at the next time point, you provide the next vector at t equal to 2, let's say. So that so the model now it has the previous value represented in a particular way, and it has the new value which is coming in like this. So here it again calculates some, it executes some mathematical function and calculates an intermediate value which is called as ht. So this is again remembered. Then the third, at t equal to 3, the next thing comes in, next input comes in. Again, it is combined with the previous values and then again stored. So when we are considering this ht, it has the, the memory from the previous steps as well as the input which is being received at that step. So it's like the whole thing, the whole sequence is being digested by your model step by step. And whatever you are providing at any particular point, it's like combining it with what it already has in memory and along with what it is receiving at this point, and the total representation it is remembering for the next step when you provide the next input. So this is called as the what is a recurrent neural network. And then there are more sophisticated forms of this, which is known as the LSTM, the long short term memory. So I will not go into the details now of what exactly LSTM is, but you can think that it has a more sophisticated way of remembering the previous input which you provided. And then there can be model neural networks which do both the convolution and this sequential structure at the same time. So that is called as convolutional LSTM or something more complicated. So that is typically used in a circumstance when your inputs are not vectors or just numbers, but they are like some special map kind of structure. So what is happening here is you are providing some some maps as inputs, a sequence of maps as inputs. So each of these at any given point of time, your input is a map. So that is a special structure. So that's on that you carry out convolution and reduce it to some kind of intermediate form. And then the next map comes in. Again, you do the convolutions and then convert it again into an intermediate structure and then combine it with the previous maps representation and so on and so forth. So that is like what this architecture is. And then there is this learning algorithm, which is basically about so your model, it has along with its current set of parameters, it has carried out some operations and given you some result. But what are these current set of parameters? So initially your model has no idea what values of these weights etc. it must use. So let's say you have initialized it with some random values or something like so based on that, your model made a prediction. Let's say you wanted to predict ISMR, so it has given you some real number and it's saying that this is my prediction of ISMR. So now you must check whether it actually agrees with what the answer you want or not. So that is where you calculate the loss function. You calculate the error by comparing the output with the predicted value. And that error might be the difference or the squared difference between those two things. And so that is the value of your loss function. But obviously I want to minimize my errors. I will have to choose the parameters in such a way that this error is minimized. So then what happens is something known as backpropagation algorithm, which is basically a very complex way in which all these parameters are updated. Each of these parameters associated with each of the edges are updated in a particular way so as to minimize this loss function. So this again happens in many iterations. In the first iteration, so initially you had all random values of these weights. Accordingly, you got, let's say, you got a large error. Then the first round of optimization will take place and all of these weights will get updated once. So you will get a slightly lower value of the error when you make the predictions with these new weights. So the function gets updated, but maybe it's still not good enough. Maybe even after the updation, it still gives you an error which is smaller than what it initially gave you, but it's still quite large. So you must carry out another round of optimization, and it takes place in many different ways. So this loss function essential, or the error, this essentially is related to how you as a scientist, as a domain scientist, evaluate the performance of the machine learning model. So it may have different aspects to it, that evaluation. One might be simply about how, whether your the results which your model gives, whether they match with your desired results or not, as far as the only number matching is concerned. But it can also be whether they are feasible or not. So let us say that it gives you a result which matches, which is not that far from the error, from your desired answer, but it is, for some reason, it is an infeasible answer. That is to say, it does not respect the physics which you want, which you know that system follows. So even though, as far as number matching concerned, the error is not much, but still you are getting an unphysical answer. So that is where what is known as a physics informed machine learning. So there, basically what you do is, you are not satisfied that loss function which you have. The standard machine learning, the loss function is just about matching your predicted value with the correct value. But in a physics informed machine learning, it's also about evaluating whether the machine learning model's prediction is consistent with the physics of the system or not. So let's say that this is the example which you are seeing. It's basically like it satisfy, you want this thing to be equal to 0. That is, this is an equation which I guess many of you are familiar with. So this is an equality. So you expect this equation to yield the value of 0 if for some choice of x, t, and u. So let's say you have provided x and t as, the position and the time as inputs, and that ML model, by whatever function it has learned, it has provided with the value of some u, which may be some velocity or something like that. So now you first of all, you must compare this predicted value with the true value, which are your observations. So accordingly to that, you have some, you get your loss by, let's say, by mean square error or something like that. But then you also see whether the predicted value, whether it satisfies this equation or not. And if it does not satisfy, by how much is it making an error? So you expect, if the answer which you gave, if the model gave was is a feasible thing, then this would have been equal to 0. But maybe it is not 0. Maybe it is some positive or negative number. So then, if it is a large number, then you can say that it has not at all been able to capture the physics. It's not. The predictions which your model is giving is unphysical. So accordingly, so you will, when you formulate your loss function, you will also include the error or the value of this function, maybe with a square or some other thing as part of the loss. So part of your loss is coming from here, that is just matching the predicted value of u with your observed values of u, but also from the physics. That is, this is called as the observation loss, and this is called as the physics loss. So both of these, the parameters of this model are now going to be optimized in a way that both of these losses are simultaneously minimized. That is, it also learns to minimize, you choose the weights in such a way that this part is also minimized, that is, it becomes as close to 0 as possible, and this u also comes as close to the observations as possible. So that is the whole idea of this physics informed machine learning, which which was discussed in yesterday, I guess, by Professor Surya Chandra. So it is often used nowadays in fluid dynamics, and I think it's also very useful to. It may be very useful to use it in climate or atmospheric sciences in general. There are of course some computational issues related to it, so it requires this kind of calculation of derivatives. So that is done with the help of automatic differentiation. So there are some numerical issues associated with this thing. So it's still a work work in progress, but I think it's a promising direction. Now, if we talk about specifically in various applications to monsoon, so now I'll try to wrap up the talk in another maybe 10 minutes or so. I won't have the time to go into the details, but I will just give you a rough overview. And for details, we have a 2-hour tutorial later. So one applications is, of course, these kinds of forecasting tasks. That is, we already have, like yesterday, we heard from Professor Rajivan about so many different approaches to forecasting of the monsoon. Now, we can, one is forecasting can be done as like seasonal forecasting, sub-seasonal, S2S forecasting, daily forecasts, and so on. It could also be all India forecasts, region-wise forecasts, even like forecasting at the lead of a gridded, you try to forecast or make a prediction of a map like this, or that is one kind of forecasting tasks. Next is improve the estimates from the models. So be the operational weather forecasting systems, or which makes forecasts, let's say a few hours or a few weeks in advance, or be it these Earth system models which simulate the monsoon, let's say for the next 20 years or something. So all of these models, as we know, that they are limited by resolutions, and the more higher the resolution, the more computationally intensive the model gets. That is, it requires more computing facilities. So now you are again, you don't want to use so much of, or you may not have so much computational facilities. So your model may, let's say, work at, let's say, 2 degree by 2 degree resolution or something like that. So now, like when it comes, like that may not be very useful at an operational scale. So you want more higher resolution forecasts. So we can do what is known as downscaling. So like in the tutorial, we will see how machine learning can be used to do this kind of special downscaling. That is, from low resolution estimates, they are mapped to higher resolution estimates, or for removing biases. So again, we know that, like earlier I showed that study which shows that the spatial distribution of rainfall as simulated by these models, they may have special biases. That is, some regions which actually receive more rainfall, the models are showing to receive less rainfall, and so on and so forth. So those are kinds of biases. So we may remove these biases with the help of a suitably trained ML model. That is, I will train the model in such a way, my inputs will be the estimates obtained from those models, and then the outputs which I will specify are the actual observations over the entire region for that particular time. So the model will basically learn to represent a function which maps the biased inputs to the unbiased outputs. So that is another approach. And then there is the task of simulations. So like the simulations right now, which are carried out by the Earth system model, so they are based on the representation of the physics of the whole system. So that the simulation, of course, it involves many different layers, the atmospheric processes, Earth processes, oceanic processes, all coupled together. But let's say I am not interested in such a huge simulation of the whole Earth system. Let's say my question is very specific. My question is, what will the rainfall how will the rainfall over Bangalore evolve in the next 50 years if we reduce or if we somehow are able to cap the amount of carbon we are emitting worldwide. So let's say I want that to do a very specific type of simulation. So in that case, I don't really I should not have to run these whole these Earth system models using lots of supercomputers. I may want to be satisfied with running some simple model which I can run in my own laptop by opening a Python or MATLAB. So in that case, I want a simpler version of this model which can do simulation of more specific things. So earlier there used to, especially in the hydrology community, something known as synthetic weather generator was very common. So there used to be some statistical models, where the rainfall, etc., is represented as a random variable, and their relations between one or two other variables is represented with some kind of conditional probability distributions. So then you just draw a large number of samples from those and you generate a sequence. So that was the approach of synthetic weather generator, but that was, you can say, was limited in the sense that only some few variables could be combined, and you could construct those conditional probability distributions, but how much, how complex can those distributions be? So it turns out that neural networks actually can allow us to reinvent those kind of weather generators, but in a much more complex way. It can provide it can again help you to define a distribution, a probability distribution over rainfall at a particular location, but using it like as a conditioned on, let's say, rainfall and many other variables over many other places. That conditioning, it can be represented, that conditional distribution can be represented by a complicated neural networks, which may allow you to do this synthetic rainfall generation, but in a much more sophisticated way than was earlier possible. So these details I will not have time to skip, but the one or two things I would just still like to draw your attention. So like earlier I was talking about this forecasting of monsoons. So this forecasting of monsoons, as you can see, like in one of the recent works which was done by Professor Bhupendranath Goswami and some of his students. So here they actually learned to they came up with a machine learning model which can actually predict the ISMR. In this case, just the one real number for the whole season. But they managed to, the input to their model was the worldwide map of some of let's say sea surface temperature, and they showed that it is possible to do this 2 years in advance. That is, if you give me they have been able to build a neural network. If you provided the spatial map of the sea surface temperature for a particular year, it will be able to give an estimate of the ISMR 2 years from them. From then on. So that is like one kind of ML based forecasting on monsoon that they have done. So here we are seeing a different kind of forecasting. Here we are not talking about ISMR as a whole, but we are talking about daily weather forecasts. So the whole thing looks somewhat like this. You provide an input sequence, let's say the amount of the amount of rainfall over India, as well as some other predictors, which they have mentioned here, the sea level pressure, these U wind, V wind, etc., which they feel as are good predictors. So they provide an input sequence of daily values of these things, and what they get is these outputs, which are the classified monsoon days. If this is what the different predictor variables for the past 3 days or past 5 days looks like, then the next day is going to be an active spell day or a break spell day or something else. So this is something like a sequential prediction problem. And then apart from this, there are also some other kinds of work apart from forecasting which can be done. So we know that there are various external drivers of monsoon, like El Nino southern oscillation is a well-known external drivers of monsoon, IOD, Indian Ocean Dipole. But then again, yesterday in some of the talks, this was mentioned that AMO, there's some processes in the Atlantic Ocean are also known to impact the Indian monsoon. So there are all these external drivers of monsoon. Now one can pose this question, like can the values of all these things, can they be used to make forecasts of monsoon? Not only forecasts, but what exactly is the relationship between all these variables and the Indian monsoon? So can we represent some kind of causal pathways? Can we say that ENSO has a direct causal impact on some other phenomena, which in turn has a causal impact on monsoon? And then is there some feedback network, like ENSO impacts monsoon, but then does monsoon also impact the next year's ENSO in some complex ways? So finding out these kinds of relation, that's called as causal analysis. So there are machine learning models which can do it. Or then there is now something known as explainability analysis. So which basically allows you, when a machine learning model is making a prediction, let's say it made a prediction, now you want to understand which parts of the input were vital in making the prediction. So let us say now as I said, let's say you have made a forecast of Indian monsoon based on the external drivers, Now you want to understand, you want to solve this attribution problem. Let's say there was one year in which there was a huge excess or huge deficiency of rainfall. Then what do you attribute it to? Do you attribute it to like that this year there was a very strong El Nino, that's why there was a drought in India? Or there are also some years, yesterday we saw so much about El Nino versus non-El Nino droughts. So if there was, let's say there is a drought over India, but there was no El Nino, then what do you attribute it to? Which other factor? So such kinds of questions can be answered with the help of what is known as the Shapley value analysis. And then there are like, I mean, all these are also questions which can be done in with the help of machine learning. Now, of course, my time is up, so I will stop here. But in the next, after lunch, we'll have this 2-hour tutorial where we will focus in details on these two specific aspects. One is the downscaling of rainfall estimates, and the other is stochastic modeling. Like we will have this have the demo session. So yeah, more at that time. So meanwhile, I'll stop, and if there are questions, I'll be happy to take them.
Thank you, Adway. Maybe a couple of questions.
Yes, sure.
Yeah. So in the introductory slides, you also mentioned like data assimilation and stuff like that you can improve using machine learning.
Yeah.
So, but we already have data assimilation in our physical model.
Yeah.
So is there a way to improve it with ML, or if there is, then how it's different than our traditional data assimilation?
Yeah. So it really depends on the data which you are receiving, let's say in real time from the satellite imagery. For like how you pull out the essential components of the of that information, how you represent it in a specific way, in a specific form, and provide it into the these models into these models in real time. So there might be certain challenges related to that. Now I am not a data assimilation person, so I cannot really go into the details of I mean exactly what aspects can be improved by machine learning. But I mean what I understand is it allows you to it allows you to a better representation of the satellite and other sources of imagery, the other sources of data, to pull out the more important aspects of it and providing it as inputs to the model.
Thank you.
You have a bit longer question. You might want to ask. If it's too long, then maybe we'll take it in.
Hello. Yeah.
Okay.
So I wanted to know about the explainable AI. There are some new techniques which explain their results.
Yeah.
So how do they do it? Is it reliable?
It is reliable. So okay, so what explainable AI does is, let's say we build this kind of neural network which we were just talking about. So they represent a lot of computation which is done in so many different steps. So but the question arises, so what exactly is the function which you are representing, and why is that a meaningful function at all? I mean physically meaningful. So that is the understanding that question is the motivation of explainable AI. Now, if you just simply, let's say you are able to write down a very a huge equation representing the neural network, that will still not make any any meaning out of it. So what typically happens is, what from explainable AI you may get two different things. One is like which parts of the input are most vital in generating the output. That is, like you throw in a huge vector or matrix as input and you get an output, but which parts of it specifically were the important factors and which were not important. So that identifying the important factors, that is one aspect of explainable AI. Another factor is, let's say for a particular instance, let's say the input was this and the output was that. So what it does is it helps you to let's say it provides you some simple rules that it tells you that I essentially focused on this variable. I saw that it's less than a particular value, and I also focused on this variable. I saw that it's more than a particular value, and I did a little bit of this and that, and finally came out with the answer. So it basically what it does is it does something very complex, but it gives you a very simple rule-based or decision tree type of a representation of what it did. So these are the two that's called basically giving a post facto explanation. So these are the two main things that are done in explainable AI.
Okay, short question.
So I understand how we can use these methods to tease out some sort of correlations, but I don't understand how you get the causality. So could you elaborate on the causality analysis?
Yeah, sure. So causality is causal inference is something which is which is a relatively new topic. So there are many philosophical questions related to causality. So there is something known as Granger causality, where you basically have two time series, and you say that one time series Granger causes the other time series. The idea is that if you can, let's say you want to predict the next value of the of one time series, let's say that time series X. So one approach might be just focus on the past values of that time series and make a forecast of what's the next value. The other approach might be, along with that past values of the time series of X, you also consider the past values of the time series of Y, and you see that way you can get a better forecast. If that happens, then you say that time series Y Granger causes time series X. That is one notion of causality. That is, it is seen purely from a predictive perspective. Allowing something or if considering something allows you to make better forecasts of the future, then you say that that is a cause of what you are trying to forecast. But it can, this has some limitations. So a different approach is related to statistical independence and so on. So there you try to see whether you carry out some statistical tests. So in yesterday, one of the speakers, I think Professor Subhimal Ghosh, he was talking about, when he was talking about those land processes, he mentioned some PCM-CIE algorithm. So that is what it really does, is it tries to find causal independence relations, conditional independence relations between what you are trying to theorize as a possible cause on what you think might be the effect. So if you carry out some statistical tests and see if there is some kind of if they are conditionally independent or not. If you say that they are conditionally independent, then you can rule it out as a possible cause. So this thing you do in multiple at different time points, that is at different lead lag relationships, and if various criteria are satisfied, then you say that this is a cause of that and this is not a cause of that. This is another approach. A third approach is intervention based causality. That is, you actually make changes in one variable and see in a controlled way, making sure that when you are changing that variable, no other variable is getting changed, and you see whether the result of changing the input variable results in a change in a corresponding change in the output variable. If that happens, then you say that there is a causal relation. So unfortunately, in the domain of climate sciences, it's not really feasible. That is, let's say you are asking a question about is ENSO a possible cause of Indian summer monsoon, or excess or deficiency of Indian summer monsoon. Now you cannot really make an intervention on ENSO and see whether the monsoon is changing or not. That's of course an unphysical experiment. But in some other but in terms, like if you have a really good climate model which you are convinced that is a perfect realization of reality, then it's possible to do, maybe that also might be possible. So these are the three, as far as my understanding goes, these are the three main aspects or main ideas behind the causal analysis.
I think the question was regarding ML, right? How do you use ML stuff for cosine?
Yeah, so essentially that only. In the first case, if when we are talking about the Granger causality, so in that case, when we are trying to predict the next value using the past few values. So like if it is related to like we can, I mean the Granger causality in the usual way means just a linear function. But now, now that we have ML, we can actually try to make a non-linear function and see if that then it can be a non-linear Granger causal relations also. Now, when it comes in the second
again,
case,
what part of the time series are you using the neural net? Are you using the neural net to do something with the time series?
yes, you can like let's say the past few values. Let's say it really depends on how far you want to go. Let's say that you think a look back. You choose your own look back period of say past 10 values or past 20 values. So those things you provide as an input to your neural network and see if it can predict the next value as the output. So that's one thing. In case of the second thing which I mentioned, the PCMCI algorithm, so like how you do these conditional independence tests and so on. So that is not really this supervised machine learning which I mentioned. It's like it may be related to the various statistical aspects of machine learning which I did not talk about. So but I mean, so there also a learning aspect can come in. Similarly, in the case of intervention based causality also.
Yeah, let's thank Dr. Mitra again for this nice talk.